Hello. So, we're going to do the topic of waves together. So, let's start. Waves can be found everywhere. So, examples of waves are water waves, which you've seen at the beach when the waves come in, light waves, and sound waves. The most known waves are water waves, which are the ones you see at the beach, for example. Now, waves are created by some form of a disturbance. For example, if you throw a stone into the water, or a duck shaking, not if you toss, for example, such as a stone thrown into the water or a duck shaking its tail into the water. So that creates a small wave. Like all other waves, a water wave has a crest and a trough. So the wave crest is at the top of the wave, while the wave trough, T-R-O-U-G-H, that's how you pronounce it, is at the bottom part of the wave. So wave crest at the top and wave trough at the bottom. Now I am going to link the notes that I'm using in the email I'm going to send so that you know where I'm following from. So now there are always two types of waves, only two types of waves. There are transverse waves and there are longitudinal waves. So when you grab a slinky spring and you move it up and down, it creates a wave that goes up and down. So a transverse wave is a wave in which particles of the medium move at right angles. This is a transverse wave. You're seeing how it's moving up and down, up and down. So that is a transverse wave. So the wave is moving at right angles to the direction in which the wave moves. So for example, from the above diagram, this diagram, energy will begin to be transported through the slinky from the left to the right. So the energy transportation is moving from the left side to the right side, from here to here. An example of a transverse waves would be light wave, heat wave, an X-ray, and a gamma wave. You don't need to know what these are for now. Now, a longitudinal wave. When a slinky spring moves from side to side, the wave is said to be longitudinal. So a longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction what does it mean? It's a bit complicated. This is a longitudinal wave when it's moving from side to side, from side to side. So an example of a longitudinal wave is a sound wave. So don't worry about this if it looks a bit complicated, but we already know what crests are. So the crests are the high point of the wave. The low parts are called the troughs. These are the low parts. The height of a crest or a trough is called the amplitude. So the height of the trough, the height is called the amplitude, where there is this green arrow here. So even over here, there would be the amplitude, over here, over here. Now the distance between two crests and two troughs is called a wavelength, and is represented by this symbol, I don't know what it's called. So, don't worry about this part and points B to G, we'll get back to that later. So, now, the frequency is the number of cycles in 1 second. So 1 cycle is made from point B to G. So 1 cycle is from point B to point G. So you have a whole wave over here. Now the frequency is the number of cycles in 1 second, the number of these that there are in 1 second. So from point B to point G. Now longitudinal waves, as you can see in the diagram, have compressions and rarefactions, they're called. Now what are these? So a compression is when the spring, as you can see, is compressed together. And a rarefaction is when the coil is not compressed. They're spread apart, so that is rarefaction. Let's go over some wave terms together. So we have the amplitude, which is the height of the wave. We have the wavelength, which is the distance between a crest and a trough. So a crest, so this is the distance. Symbol of wavelength is this. Now, the frequency is the number of complete waves per second. Hertz is the units of wave frequency. So 1 hertz is equal to 1 wave per second. Don't worry about this for now. Now we have, sorry about that, we have wave speed. Now, wave speed depends on the medium in which it travels. So it depends on the material in which the wave is traveling. So in a given medium, the speed of a wave is 3 times 10 to the power of 8 meters per second, and it is always constant. So wave speed is calculated by the equation wave speed equals frequency times the wavelength. And we'll come back to these equations soon. Now, periodic time, the time taken to complete one wave. It's measured in seconds, and it's measured by using the following formula. So time equals 1 all over frequency. Work out a few of these together. Now, I'm just going to copy the question and paste it over here. Now, a wave has a frequency of 2 Hertz, and I'm going to highlight that, and a wavelength of 10 centimeters. What is the speed of the wave? Now we know that wave speed is equal to the frequency times the wavelength. So we know that the frequency is 2 Hertz times the wavelength, which is 10 centimeters. Now I think we'll have to change the 10 from centimeters into meters, because the units of wave speed are meters per second. So I just checked. It has to be in meters. So 10 centimeters needs to be changed to meters. So 10 centimeters division by 100, yes, because there are 100 centimeters in 1 meter. So this would come 0.1. Sorry. So let's work it out together. You have 2 times 0.1, so 2 times 0.1, and the answer is equal to 0.2. Now we know that the units are meters per second, so the answer is 0.2 meters per second. Now another question. A radio station produces radio waves of frequency 200,000 Hertz and a wavelength of 1,500 meters. Now, what is the speed of the radio waves? Now we know that wave speed is equal to frequency times the wavelength. So we know that the frequency is 200,000 Hertz times the wavelength, which is 1,500 meters. Now the answer to that is, let's work it out, 100,000 times, how much was it? 1,500. 200 million. So the wave speed is 300 million meters per second. So another station produces waves at 500 kilohertz. Kilo, this is important. What is their wavelength? So we know that wave speed is equal to the frequency times the wavelength. Now, so that the wave speed is 300 million meter per second. So frequency, we know that the frequency is 500 kilohertz. Now I have to change 500 kilohertz into hertz. So this would be times 1,000. So 500 times 1,000 is equal to 500,000 times the wavelength, which we have to find. Now we have to make the wavelength the subject of the formula. So what's going to happen? We have to take this to the other side. So the wavelength is equal to, so what are you going to take to the other side? You're going to take the 500,000. So you're going to take 300 million divided by 500,000, because the times became a division when it went to the other side, is equal to the wavelength. Now let's work it out. The answer is 600 meters. So that's the wavelength. So what you need to know next is refraction. So what is refraction? Let's make it a bit bigger. Refraction is the change in direction of a wave passing from one medium to another. So it is a change in direction. So let's see a picture of a refraction. This is an example of refraction. I hope you can see it properly. For example, this is a light wave passing through a pane of glass. It's moving at this direction, and when it hits the pane of glass, it changes direction. You're seeing how it's moving this way, and then it's moving this way. This is what refraction is. That's what you need to know.